Quantum computing requires quantum networking to reach its full potential. But there are engineering challenges to overcome, especially in building repeaters to extend entanglement between qubits. We dive deeply into quantum networking and its future, including how it will affect interconnect, in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guests today are co-founders of memQ. We have the CEO, Manish Kumar Singh, and we have the CTO, Sean Sullivan. Gentlemen, welcome to the show.
Thank you. Happy to be here.
Thank you.
Yeah, so before we roll deep into what you all do, I would love it if you could just tell our audience a little bit about how each of you made it into the QIS field in general.
Absolutely. So for myself, I took a very nonlinear pathway. I did my undergrad in chemical engineering, then worked in the semiconductor industry for almost 5 years, and then decided to get a PhD. And by the time I came here for my PhD, the winds had changed and a lot of opportunity had started coming up in this new field. So that's where I chose to do my PhD. And it was related with some of the work that I had done, meaning we were trying to develop a platform that will allow you to take advantage of the same methods that goes into the making our silicon chips and use those to make qubits. So my PhD thesis, in those words, was to develop a method that would allow us to do solid-state qubits on a silicon platform. And worked on it for about 5 years. 3 years in, I started working with Sean, and around the 4th year, we got really lucky with the materials that we were working with. And from there, memQ started.
Okay. And Sean, how did you find your way to silicon qubits back then?
Yeah, so I started out doing, material science and engineering, similar to Manish. But I was more focused originally, before I started my PhD and everything, on actually energy conversion, sort of for greener technologies. And a lot of the materials and things that I was working on, you actually started getting into the quantum properties to really engineer these materials at, sort of the atomic level, to maximize things like efficiency for energy conversion and things like that. And so I started really getting more into sort of the quantum mechanical, quantum engineering aspects of material science at that point, and using optics and things like that to characterize these things. And so I kind of pivoted a little bit after my PhD from, focusing on the quantum materials for energy conversion to focusing on quantum materials for quantum information processing. So going from energy transport to information transport. And so that's why I joined, my postdoc at Argonne National Lab. There's a lot of great experts in the quantum information science field here in Chicago. And so I was really excited to join, the group of David Oshalom and Joe Hermans at Argonne. And that's where I started working with Manish, where we were really tackling this problem of making, materials and devices for quantum communication applications. So.
Yeah, that's great. Oh, I'm going to be visiting Chicago on my actual birthday, and I'm going to be spending it at Argonne.
Oh, really?
So if that's not
okay.
the nerdiest way to spend your birthday, I don't know what is. But yeah, that'll be coming up soon. So instead of then taking this research and just publishing a paper and going into academia, what made you guys say, nah, we're gonna form memQ? How did that get going?
The University of Chicago provides a very good ecosystem it has like a lot of departments. It has a great business school, and all of that like allows you to explore all the ideas that you want to explore. One of the things that I was really interested in is how do you take a technology from the lab and to the market? And having the business school right there, I got to interact with a whole number of VCs, professors, MBA students, and learned how to think about these, these game-changing technologies or these breakthrough technologies that come about. Like, how do you even go about thinking whether or not it would become something that is useful to some, that somebody will be willing to pay for in 5-year time? So, having been through that framework, by the time we made our discovery, I was convinced that we had made that final breakthrough needed for this platform that we were developing to become the platform for quantum communication. And from there on, it was customer discovery, and that kind of led us to where we are today. And of course, we did publish our papers and along the way. But what we also did importantly was file for patents.
Yeah, that definitely enables the commercial engine moving forward. So let's talk a little bit about those keywords you said, right? So your discovery and the platform. I guess let's give everyone a sense of what you're hoping to build here.
So one of the toughest challenges right now is how do you send quantum information over longer distances? Now, when you think about quantum information, it's not just about sending photons. It's about this fundamental resource, in a sense, quantum entanglement. How can you send it over longer and longer distances, right? And that is the resource it's fundamental to computing, it's fundamental to communication, it's fundamental to sensing. And by these three, I mean fundamental to quantum versions of these words. And so what our platform enables is we work with what's called the rare earth qubits in order to store the quantum states for longer and longer periods of time so that we can extend this entanglement. Like, if we are able to, and it has been demonstrated, we can connect A and B, we can connect B and C, we can connect C and D. But in order to connect A to D, you need to be able to store information at B for a long period of time, C for a long period of time. And by long, I mean it could depend on the application. It could vary from a few milliseconds to a second. And that's good enough to send the quantum information there. So that's the heart of the problem we are trying to solve.
Okay. So what are those rare earth qubits?
For that, I'll direct
I figured
this
one was
question
going
to
to
Sean.
Sean now. Yep.
Sure, yeah. So we're specifically working with erbium ions. So the rare earths are like a grouping on the periodic table, basically. Like, you have, when you look at the periodic table, you have those two lines that are kind of at the bottom, those two rows that are at the bottom. Mm-hmm. The rare earths are kind of like in there. And we're focusing specifically on one. None of these are radioactive or anything. We're talking about the top row here. So this is erbium, which has actually been used a lot in the communications industry for a long time for making lasers and things that are used in fiber optic networks. And the reason why is it produces light, emits photons that are at like a very specific wavelength that's kind of in the near infrared, so just beyond what you can see towards the red, that transmits through optical fibers really well. So they're not absorbed, they go long distances, no problem in these optical fibers. And what's exciting about that is like we have this way of producing these photons, which is great for quantum information for communication. But there's also a really cool property about the electron structure of the ions themselves. And when they form in matter, in solid state matter, you can have individual electron spins at different energy levels that are like, so you hear things about spin qubits, but this is basically a spin qubit that you can interface with light. So you can excite and read out and do all of that thing with light, and you can make that light go through telecom networks. So there's some really cool stuff that you can do with that. That's for both communication and memory storage, those types of things.
So when people hear about quantum networking, I mean, all their lives, well, maybe not all their lives, but that when they think of networking before this, it's very set things, right? You've got this protocol, you're doing something on your computer, and you're sending just pure information out there. It's not information that's like live. It's not like a calculation that's in progress or anything. It's like, hey, I wrote this thing and I send it out as bits, right? And that gets moved around and routed to the right place because of the networking stack and all that good stuff. So when people try to visualize quantum networking, it's really, really different. So I didn't know if you just wanted to give a little high level to help listeners understand why it's so different and what its potential benefits are then.
When it comes to quantum communication, right? So the heart of it is, how do you send entangled photons over very long distances, right? That's the problem. Now, an analog here would be like, say, you can generate a voltage by running, like using hydroelectric plants or something. You can have a voltage generation, but you got to send it to the point of consumption in a sense, right? For that to happen, there are losses there too. If you use 220 volt to send it over long distances, you lose all the current that you have along the path. Like there will be resistance, you'll lose everything on there. For that to be able to send that over long distances, you need to you need a transformer, right, to up the voltage to 33,000 kilovolts, I think, is what's currently used. So that is the key thing there that enables you to distribute electricity to longer and longer distances. When it comes to entanglement, we can do wonderful things with entanglement today, like very beautiful experiments have been done. But in order to send it over longer and longer distances, you need two things. You need to be able to store it at intermediate stations. And that is important because you can only send single photons, and you cannot copy and amplify it because that destroys the quantum state. So the same thing that gives us the promise of unconditional security also brings this challenge that it's very difficult to send single photons directly over long distances because they get absorbed as they propagate. So that's a central challenge there. And in order for any platform to solve that problem, you need to be able to transmit at the telecom wavelength, like Sean explained, and you need to be able to have like thousands of these signals, or for the lack of a better word, thousands of these communication qubits at every base station, right? So from our estimates, these base stations would be somewhere between 50 to 80 kilometers apart. And in order to get a meaningful rate between them, you need thousands of qubits at each station. So that's where the platform needs to be scalable so that you can have thousands packed on a single chip. And then it needs to have this memory capability. So you can store it while you connect the other bit. Like I said in the previous example, say A and B get connected. Now B and C need to get connected. And these qubits at B then undergo this special operation called an entanglement swap. And that is what ends up connecting A and C. Magic is that A never sent anything to C. But this entanglement swap ended up connecting A and C now. So now A can send information to C without actually sending an information directly. So that's where they can use the entanglement as the resource that gets used up once you transfer information from A to C.
Yeah, that's easy to visualize. And you're avoiding the no cloning principle this way.
Exactly.
Yeah.
Just to draw an analog, right, with the digital communication that we think of now, right? Like everything is converted into bits and sent over communication links. But this is kind of almost more of like an analog kind of communication, right? Like you're sending the raw qubits, in a network that's able to speak the language of quantum physics, rather than having any sort of translation to digital packets, and then you can use algorithms to unpack that. You can't really do that in quantum physics. I mean, you can do measurements in like a measurement basis, and at which point you sort of collapse that wave function. But you need to preserve this quantumness over the entire channel. So that's kind of how it's a little bit different.
Basically, these are like repeaters, kind of, and exactly. They're simplified quantum computers that do one operation, the entanglement swap.
Well, like that's how we envisioned the first generation, right? So I think Professor Jiang at the University of Chicago, he came up with this generations of repeaters about 7-8 years ago, where the first generation is only capable of doing what you just said. And then as you add more capabilities on it, right? So if you're sending information from A to B, there is a very good chance that you lose photons. It's a probabilistic process. So you're going to lose some of your qubits. The information is going to, you're going to get some errors over that channel. Now you need to be able to correct for those errors. In order to do that, you need more capabilities at these nodes. So these nodes now get up to the second generation where you can correct for some of these errors. Then there is a third generation that is defined as where you can correct for all the errors, propagation errors, gate-based errors, loss errors. And at the third generation, you're essentially working with these very specific quantum computers in their own right. So if you can do quantum error correction and you can do manipulation with a bunch of qubits, what you have is a quantum computer essentially. So with the third generation, what you have is very specific, specialized quantum computers at each nodes that are dedicated on information transfer. And that's where our vision for memQ kind of aligns really well. The platform that we are developing, it's not just memory, it's not just entanglement. It's about developing a whole system on a chip where you can have, like in generations, we prove a set of capabilities, we add more on it, and we complete the full arc with these quantum computers at each base station, really.
So those generations seem to match and map perfectly to what we hope to get out of quantum computers in general, right? Like we're hoping to get, lower errors, and then error correction, and then, so you're hoping to kind of like chart the progress along the way. And networking has always been mini computers, right? Like a router is a mini computer. You could run Linux on it or something. You could do whatever, it's like, so it's a similar approach. So what other technical challenges do you have to overcome right now?
Sean, would you like to talk about the coupling challenges? I think it's fair.
Exactly. Yeah, so this has application beyond just quantum networking, but in interconnect in general, which is really moving towards photonics, using light to transmit information quickly. And so one of the key challenges is taking light that's in a fiber or in a fiber network and putting it onto a chip which may be running like silicon photonics or some sort of photonic circuitry. And the reason why that's challenging is these are different materials. Light propagates them inside them in different ways, like in silicon versus a silica fiber. They have very big different refractive indices, things like that. So you have a very large, almost like an impedance mismatch between your fiber and your chip. And so you need to come up with, ways to sort of carefully and, slowly adapt getting light from the fiber onto the chip and vice versa. And so there's been a lot of progress in that. But one of the challenges in quantum photonics and quantum, systems that are using light is a lot of these operate at cryogenic temperatures where it's cold. And you stick this in a cryostat. You cool it down to 4 Kelvin, or for some systems, maybe you have to cool it down below in a dilution refrigerator. And you get all these shifts that happen, with temperature. Things contract and move around, the refractive indices, so the materials change at different rates. And so there's really not a currently good solution for getting light on and off chips in a way that, has high efficiency at cryogenic temperatures, that you can make a package, stick this in, cool it down, and expect it to work as you would want. So that's one of the things that we're focusing on.
So basically, like if the efficiency drops to 50%, you lose half of the photons that are coming out.
Mm-hmm.
So one thing that Sean likes to say is every photon is sacred, and we we need to take care of every single photon that comes out.
Yeah. Okay. The BB84 protocol doesn't consider everyone sacred, but okay, that's fine. So what kind of innovations do you feel you'll be bringing to this? Like, so obviously a lot of people are looking at quantum networking. What do you think puts you in separates memQ here?
Right. So the key innovation has been this light matter interaction that we can engineer, and that we are building upon. So the ability to see rare earths have very good spectroscopic properties, and they've been under investigation for 40, 50 years. Mm-hmm. And as Sean said, they've been used in optical communication networks, lasers, and whatnots. In order to get the properties that you get in bulk crystals in a thin film, we have developed engineering methods that allow us to transfer some of those properties and engineer the same properties that we see in bulks, or at least approach them. Being able to do that is a key breakthrough. And what memQ aims to do is build on that and engineer this to a point where you have the 1,000 devices that we were talking about. Right now, no platform can make 1,000 devices that are very similar to each other. We believe that our variations are small enough that we can have 1,000 devices that are very similar to each other. And by adding additional controls, we can make them exactly similar to each other. And that's where the true power lies.
Yeah, so really just leveraging all the decades of expertise of the microelectronics industry. We both have some experience with that, Manish in particular, but that's something that for large scale processing scalability that we really want to try to leverage. And so we've chosen a system that we think can work really well for that.
So what about the impact of protocols on a platform like this? So let's say we want to use this for interconnect one day. Mm-hmm. Let's say we want to have 2, 6, 10, however many quantum computers behave as one. There's obviously going to have to be some, and a few companies are working on this already, like Entangled Networks. They're trying to figure out what that protocol is that lets these machines behave as one, over distances or whatever. So how would that impact your devices? Like, would you have to build something specially for that? Do you have to already start giving thought to like how these are going to be used maybe one day to accomplish that magic of, entanglement on multiple systems?
The beauty is that at the hardware level, it's as long as you can, as it exists right now, at the hardware level, as long as you bring in a photon, whatever device you have, as long as it brings in a photon, you can plug into this network. If you're trying to connect a microwave computer, like the kind of computers that Google and IBM and Rigetti and all of them are developing, you want to plug them, and you'll need what's called a transducer. You need to be able to convert the microwave photon to an optical photon in order to plug into what would be memQ's networks. As long as you can do that, the hardware level itself, it's agnostic to what computers are coming in. It treats every photon as the same.
Interesting. Okay. So with the right software, protocol, whatever, it might be possible to do interconnect between like a transmon and a trapped ion or something, if they're, if they can connect your network ultimately.
Exactly. Yeah.
Yep.
Are you guys working on anything in the field of interconnect? Are you trying to experiment with those aspects of it, or are you just kind of leaving that to other folks to use your architecture?
So our core capability is in the light matter and the memory division in that sense, right? So we're trying to develop that core of our network. And that's the primary problem. The secondary problems are these interconnect problems, which we are not the best at right now. So if other solutions come upon, we will just make sure that it adapts to our network. but the focus is to develop the heart of the network right now.
Okay. What kind of security concerns do you think there'll be with quantum networking? So you build something like this, what kind of vulnerabilities will there be? I've been involved in that side of it for a while with the early QKD experiments and things. There have been some pretty funny hacks in the early days with, flooding laser light and things like that. So what do you anticipate would be some kind of concerns?
One of the things that you just mentioned is like in any of these networks, if you can flood it with light, you can just like stop all sorts of communication.
Yeah.
So that's a major challenge. There are some solutions that are under research, but that I'll acknowledge that as a challenge.
Yeah, definitely.
Yeah, definitely. That is a major challenge, and QKD in general is seen as vulnerable to a variety of different attacks, and like Manish was saying, there are maybe workarounds that you can come up with, and that's from the purely security standpoint. But I think in terms of like enabling things beyond just the cybersecurity aspects, like you were talking about interconnect and distributed quantum computation, this is the way to go, where you're really sending flying qubits over a long distance. And so we have to think about ways that, okay, maybe if we want to avoid someone doing basically a denial of service on our distributed quantum computation, then maybe we have to come up with some clever ways of shunting things around, changing network topologies, things like that quickly. But yeah, I think that's definitely an open problem that a lot of people are working on.
And it's not really a privacy concern. It's like, what are you you can't really eavesdrop on a qubit and have it mean anything. Like it's
exactly. It's exactly.
Yeah, you'll just damage the computation, but you won't actually learn any information.
What's going on?
Yeah, I'll just add that one way to think about it, if instead of a linear topology, like you're thinking about a network that has like many connections, you can essentially like cut off that region where like an attack has happened, and then find out another route to deliver the entanglement.
So these advances that you're making, you're hoping to make in these like miniature quantum computers that are, they're almost like ASICs, right? They're, they like to have this one application that they're built to do. Right. Do you see any of this kind of filtering upstream to other, types of computing development? Do you anticipate like, hey, we're doing such a great job at this that maybe you want to implement this in just your, general fault tolerant kind of systems one day? Do you see anything like that coming out?
Yeah. So, I mean, I think kind of as I maybe alluded to before, there's a lot of interest in going towards photonics. Mm-hmm. So we're developing a lot of like laying the groundwork for a lot of integrated photonics technologies. So using photonic chips for low power computing, whether this is just classical computing and you're doing some sort of Fourier transform operation using photonic elements, but you could do this with really low power. So getting light on and off chips there, that's a place that can get a lot of benefit. And yeah, I don't know, Manish, did you have any other thoughts here?
Yeah, no, absolutely. So the methods that we're developing, right, say our methods for getting entanglement on chip, getting a whole number of devices that are very similar to each other. Now that maps to the quantum computing effort that focuses on photonics. There too, the self-similarity of photons is a very, very important part. So that section kind of maps to any of those problems that are being solved using this. The ability to error correct, for example, will map directly to any photonic platform. Like Sean said, it even maps to non-classical platforms. But especially in quantum platforms, the error correction there are companies out there that are developing quantum computers out of these photons. And these sections, these dedicated, say, a memory module, for example, could map onto that. Right now, if I understand correctly, the memory is just a loop of fiber. And that's good enough to introduce a delay into what they're trying to develop. What we are trying to build has the memory capability at the center of it. We're not trying to work around the problem, but we're trying to solve that problem because it's very important for the quantum communication application. But a memory application that gets developed for quantum communication can also map to quantum computation. Because when you're loading like very large data sets, you need to be able to store it. You need to be able to have these registers that can store these quantum results for a while. And then you load new data, perform computation, reload these, and so on.
So it could maybe even impact like the depth of circuits or something like that going forward in quantum computers.
Yeah, or maybe new types of algorithms quantum algorithms that utilize something like a quantum memory, which is not is typically used in when you look at a normal algorithm today.
Nice. Yeah. Okay. And so when would you anticipate having like a basic network running that companies can finally plug into? I know that's probably the $1 billion question, but yeah.
I'll try and answer a simpler version of that question.
Okay.
So we expect to have our devices plug into the Chicago quantum network, right? So there's a test bed that already exists in the Chicago area. It's about 124 miles. And that would be the perfect place to test out memQ devices, right? And as we build on, if it works on that network, then we can bring on more folks who can use our devices, our capabilities on this test network in order to build more applications and test out the technology. So the first, we see these in 3 different waves. The first one, we are pretty hopeful we'll get to a prototype of one of the components by the middle of next year. Okay. And another one in another 18 months or so, and a network prototype where we are actively managing entanglement across over a network like this, something like 24 to 30 months.
Oh, wow. Okay. So there could be some real traction here. And are there any other types of projects that you're working on that you wanted to talk about before we close, or are you really focused on that goal right now?
Now, the key for a young, small startup is to stay focused on one problem that we know how to solve very, very well and solve it. And then we grow the team and focus on other the second order problems too.
Yeah, absolutely.
So very focused right now.
Yeah, I know this is going to be very critical to the success of QIS in general. I'm sure of it, having networking right. So I'm pretty excited to see what comes out of this. So thanks so much for both of you taking the time to come on down.
Great. Thanks, Konstantinos.
Yeah, absolutely. It was a pleasure chatting with you.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today in case things got too nerdy at times. Let's recap. Quantum networking allows for entanglement between qubits to be extended across great distances. Doing so has some significant technical challenges. One of these is the no cloning principle of quantum mechanics, which prevents an entangled state from simply being copied. Instead, we have to use entanglement swapping. For example, a qubit from a quantum computer, let's call that point A, entangles with a qubit in a quantum repeater, point B. That repeater is an application-specific quantum computer of its own, tasked with entanglement swapping. The repeater at point B will entangle with another repeater further down the fiber, or point C. This process continues until it reaches another quantum computer or sensor, completing the circuit. This could allow a qubit from point A to entangle with, say, point J. Quantum information is protected from eavesdropping by its, quantum nature. An observation made on such a network will destroy the state. We're familiar with this principle from years of QKD research. However, like QKD, we know that denial of service attacks are a real possibility via flooding fiber with lasers, for example. Protecting against such attacks will represent the first type of security control needed in quantum networks and repeaters. memQ is working on making these repeaters a reality on the Chicago network testbed within 2 to 3 years. They are building the rare earth silicon qubits that handle the swaps and quantum memory for the device. One day, Protocols like interconnect can work with these systems to allow multiple quantum computers to work as one, as regular listeners have heard discussed on this show before. If you're excited by the future of quantum networking and want to be a part of memQ, the company's hiring. Check out their website in the show notes for more information. That does it for this episode. Thanks to Manish, Kumar, Singh, and Sean Sullivan for joining to discuss memQ and quantum networking. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on Twitter and Instagram at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.